Today, we're counting down the top 15 new breakthroughs in quantum computing, all backed by credible updates this year. Stick around until the end, because the number one breakthrough is something scientists have chased for decades. Before we dive in, let's quickly ground ourselves. What's quantum computing? A normal computer thinks in O's and ones, like a switch that's either on or off. A quantum computer can be both at once, trying many possibilities at the same time. That's why it can tackle puzzles like drug discovery, climate modeling, or data security that overwhelm classical machines. Now, let's start the countdown. Number 15, climate and energy modeling with quantum algorithms. Running a power grid is like juggling thousands of flight schedules. The number of possibilities explodes. In 2025, IonQ and Oak Ridge tested a hybrid quantum classical solver on this very problem, scheduling 26 generators across 24 hours using a 36-qubit system. At the same time, researchers explored quantum solvers for tsunami and fluid flow equations. These aren't just abstract demos. They point to better renewable energy planning and more accurate climate forecasts that classical machines struggle to handle. Number 14, drug discovery acceleration. Designing new drugs often stalls at the molecular simulation stage, figuring out how protons fold or how RNA structures behave. In 2025, IBM and Moderna used IBM's Heron chip to model RNA structures up to 60 nucleotides, while IonQ and Kapu Quantum simulated protein folding up to 12 amino acids. These are still small systems, but they chip away at the slowest steps of drug R&D, hinting at a future where vaccines and treatments can be developed faster. Number 13, DARPA's US2QC program. Quantum computers today are powerful but noisy. Too many errors creep in. That's why fault tolerance is the holy grail. Systems that can detect and fix their own mistakes. In 2025, DARPA pushed Microsoft and PsiQuantum into the final phase of its US2QC program, where the goal is no longer theory, but building and validating a useful machine. Coming from the agency that once seeded the internet and GPS, this is a clear sign that fault-tolerant quantum computing is becoming a national priority. Number 12, quantum interconnect breakthroughs. Instead of building one gigantic quantum chip, researchers are figuring out how to link smaller ones together, just like classical data centers do today. In 2025, Oxford scientists connected two ion trap modules with light, teleporting a quantum gate at 86% fidelity, and even running Grover's algorithm with 71% success across both. Meanwhile, superconducting teams built chip-to-chip links with 99% efficiency in under 100 nanoseconds. These advances make modular quantum data centers a lot more realistic. Number 11, optical tweezer arrays for neutral atoms. Picture thousands of atoms held in place by beams of laser light, like tiny marbles in an optical trap. In 2025, Caltech researchers scaled this to over 6,000 atoms, with 12-second coherence times and greater than 99.99% accuracy when reading them out. On smaller arrays, teams demonstrated 99.5% 2-qubit gate fidelity across dozens of atoms. Neutral atoms now combine scale and precision in a way that puts them among the strongest contenders for building million-qubit machines. Number 10, Pascal expands to Saudi Arabia and South Korea. French startup Pascal, a leader in neutral atom quantum processors, isn't just building chips in Europe anymore. In 2025, it announced manufacturing expansions to Saudi Arabia and South Korea. That might sound like business news, but it matters. Scaling quantum isn't only about physics, it's about supply chains. By planting roots in multiple regions, Pascal is turning quantum into a global industry with production hubs, one of the clearest signs this tech is moving out of the lab. Number 9, D-Wave simulates magnetic material dynamics. Modeling magnetic materials, tracking how billions of spins interact, is nearly impossible on classic supercomputers. In 2025, D-Wave's quantum annealer handled this complexity, simulating the dynamics more efficiently than top classical methods. It's a rare case where quantum showed practical advantage, not just theory. And while annealers differ from universal quantum computers, their knack for solving physics-heavy problems makes them valuable tools in condensed matter research and material science, where better models mean better tech in the real world. Number 8. Certified randomness on Quantinuum's H21. Randomness sounds simple, but it's the backbone of encryption, secure communication, and even finance. In 2025, researchers from JP Morgan, Quantinuum, and US Labs proved that quantum can deliver it for real. Using Quantinuum's 56-qubit H21 trapped ion system, they ran a certified randomness protocol, producing numbers mathematically guaranteed to be unpredictable. That's a first. Instead of trusting chance, we can now prove randomness itself, laying the foundation for more secure systems in the digital world. Number 7. QEra's magic state distillation breakthrough. For 20 years, quantum scientists have said the same thing. Without quantum state distillation, error-corrected quantum computers are impossible. The process takes messy, noisy quantum states and distills them into one reliable, high-quality state. In 2025, QEra finally pulled it off at scale. That's huge. It shows fault-tolerant quantum computing isn't just theory anymore. With this building block demonstrated, we're closer to machines that can run long, useful algorithms without collapsing under noise. Number 6. D-Wave simulates false vacuum decay. Here's one that sounds straight out of science fiction. In 2025, D-Wave used its Advantage system to simulate false vacuum decay, a phenomenon in quantum field theory describing how the universe might jump between energy states. Classical supercomputers can't handle the math, but a quantum annealer could. This wasn't just an engineering demo, it was tackling a fundamental physics problem. It shows quantum computers aren't limited to industry tasks. They're starting to probe the very laws that shape our universe. Number 5. Google's Willow processor, 105 qubits. Google's Willow chip, a 105-qubit superconducting processor, was stress-tested in 2025 and delivered something the field has been chasing for years: below-threshold error correction. Instead of errors multiplying as more qubits were added, Willow showed the opposite. Error rates dropped. That's a turning point. It proves that scaling can actually make quantum computers more reliable, opening a path toward machines that can run long, useful algorithms without collapsing. If sustained, Willow could be the bridge from experimental devices to practical, fault-tolerant quantum systems. Number 4. Fujitsu and Riken's 256-qubit quantum computer. In April 2025, Fujitsu and Riken launched a 256-qubit superconducting quantum computer, quadrupling their earlier 64-qubit system. It's now the most powerful quantum machine in Japan and puts them on track for a 1,000-qubit system by 2026. Beyond the numbers, it signals something bigger: Japan entering the global quantum race in a serious way. For years, the US and Europe dominated. This leap shows Asia is positioning itself as a heavyweight in the field, and it highlights how quantum leadership is becoming a truly international competition. With more regions building advanced hardware, the pace of progress accelerates worldwide. Number 3. Rigetti's Anka-3 with 99.5% fidelity. Rigetti's Anka-3 made waves in 2025 with an 84-qubit superconducting processor that achieved 99.5% 2-qubit gate fidelity, the highest ever on its platform. Fidelity is the lifeblood of quantum computing. It tells you how often a quantum operation works as intended. At 99.5%, Rigetti is closing in on the threshold needed for fault-tolerant systems, where computations can be strung together reliably at scale. This progress matters because it proves superconducting qubits, often criticized as too noisy, are still advancing and holding their ground against trapped ion and neutral atom rivals. For industries eyeing quantum for optimization or machine learning, Anka-3 shows that superconducting hardware remains a serious contender for real-world applications. Number 2. The UN declares 2025 the International Year of Quantum. Not all milestones are technical. In 2025, the United Nations declared this is the International Year of Quantum Science and Technology, marking 100 years since the birth of quantum mechanics. Why does it matter? It shines a spotlight on quantum worldwide. Governments, universities, and industries are now encouraged to collaborate and invest at new levels. It's a recognition that quantum is no longer just a niche pursuit. It's a field with global impact. Number 1. Microsoft's Majorana 1 topological qubit chip. At number 1 is Microsoft's Majorana 1 processor, unveiled in February 2025. It's the first chip designed around topological qubits, which are expected to be far more stable because they're naturally shielded from many sources of error. Built from a new topoconductor material, combining indium arsenide and aluminum, the chip currently runs only a few qubits, but the design is meant to scale. In principle, millions of hardware-protected qubits could fit on a single chip. That would slash the overhead needed for error correction and make large-scale quantum computing practical. Experts are still debating whether Microsoft has conclusively shown genuine Majorana states, but if validated, this marks a turning point that could redefine the future of the field. From climate modeling and new drug discovery tools to certified randomness and topological qubits, 2025 is stepping up as a turning point for quantum computing. If you've made it this far, let us know what you think in the comment section below.